You know that feeling when you're using an AI like ChatGPT and it writes something that just feels like magic? Well, it's not magic. It's actually one of the most important ideas in technology today, and we're going to break down the engine that makes it all possible, the transformer.
So, how in the world does a machine go from just being lines of code to understanding the nuance, the creativity, the art of human language? Well, the answer isn't some single lightning bolt of genius.
Instead, it's this brilliant story of innovation. It's about researchers solving one puzzle after another, with each solution building on the last, to teach computers how to speak our language. So let's walk through that story step by step.
Okay, so the very first hurdle, and it's a big one, is that computers don't speak English. They don't speak any human language. They speak math. They only understand numbers. So the first question is, how do you turn a word into a number? Well, before a model can even begin to think about what a sentence means, it first has to chop it up into manageable pieces. This first step is called tokenization. We just break a sentence down into these little things called tokens. A token could be a whole word, maybe part of a word, or sometimes even just a single character.
All right, so how do we represent these tokens with numbers? The first try, something called one-hot encoding, was pretty simple, but honestly, it was flawed. It basically treated every single word like its own little island, giving each one a unique ID. But that meant the model had no idea that king and queen were related. To the model, they were just as different as king and carrot. Not very useful. The real breakthrough was something called learned embeddings. Now, instead of islands, I want you to picture a giant map, where words with similar meanings are placed close to each other, like neighbors in a city of meaning.
And this is where that map idea gets kind of mind-blowing. Researchers discovered you could actually do math with these word coordinates. You could take the vector for king, subtract the vector for man, add the vector for woman, and you would land almost exactly on the vector for queen. I mean, wow, this was huge. It proved the model was actually learning the relationships between words. So, problem one solved. But of course, that just led to the next big problem.
Think about the word bank. In I sat on the riverbank, it means one thing. In I need to go to the bank, it means something completely different. The problem is, those learned embeddings we just talked about are static. They give bank the same coordinates every single time. So how does a model figure out context?
The next big idea was the recurrent neural network, or RNN. An RNN works a lot like how you and I read a book, one word at a time, in sequence. As it reads each new word, it updates this kind of short-term memory, a hidden state, that keeps a running summary of what it's seen so far. So the meaning of the word bear is shaped by the words, a cute teddy, that came right before it. Finally, the model was starting to get context.
Now, RNNs were a huge step forward, no doubt, but they had a critical flaw. They were pretty good at remembering the last few words they saw, but they really struggled with long-term memory, especially in long sentences.
You know when you're reading a really long, complex paragraph, and by the time you reach the end, the details from the beginning are kind of fuzzy? Well, RNNs have the exact same problem. There's a technical name for it, the vanishing gradient. But all it really means is that the influence of the first few words just fades away until they're basically forgotten. To truly understand language, we needed a better memory.
And this, right here, brings us to the core idea that changed everything. Researchers started to think, what if, instead of trying to cram the meaning of an entire sentence into one constantly updated memory, what if we just let the model look at all the words in a sentence at once and decide for itself which ones are the most important?
In 2017, researchers at Google published a paper with this incredibly bold title. It introduced the transformer, and its central idea was a mechanism that just completely revolutionized the field. They weren't just improving on the old models. They were proposing a whole new way of thinking about the problem.
And this core idea is called self-attention. And honestly, it's like giving the model a superpower. Instead of reading in a straight line, it can create these direct links between every single word in a sentence, all at the same time. So when it's processing the word bank, it can simultaneously look at river or money, no matter how far away they are in the sentence, to build a truly context-aware meaning. It's like being able to instantly flip to any chapter in a book, not just the last page you read.
So how does this actually work? Well, at a high level, it uses this clever little system of queries, keys, and values. Think of it like this. The word we're currently focused on asks a question. That's the query. It then looks at every other word in the sentence, and each of those words has a label, kind of like a title on an index card. That's the key. The model compares its question to all the labels to find the most relevant ones, and once it finds a match, it pulls the full content from that index card, the value, to enrich its own meaning. And it does this for every single word, all at the same time. It's just brilliant.
This self-attention mechanism is the incredible engine at the heart of the transformer architecture. It's what allows the model to build this amazingly rich and deep understanding of language, all without having to process words one by one in a line.
So how does this engine fit into the whole system? The transformer really has two main parts. First, you have the encoder. It reads the entire sentence you give it, let's say in English, and uses self-attention to build that deep understanding. Then you have the decoder. Its job is to generate the output, say in French. And as it writes, one word at a time, it's constantly paying attention to both the encoder's understanding and the words it's already written. This is how it creates text that is so coherent and so accurate.
So let's just recap that whole journey really quickly. We started by turning words into numbers using embeddings. Then we gave them context with RNNs, but that created a serious memory problem. And finally, that led us to the huge breakthrough, attention, the mechanism that lets a model weigh every word simultaneously, which became the powerful core of the transformer.